Alright. Pardon me. I had wanted to go ahead and get started by going over the old exam. Several of you have asked me questions about that. So, give me a second. There we go. All right. If you've seen me do this before, you know I have about 18 different computer screens open, so we just kind of have to do one at a time. Okay. All right. So these were some nomenclature questions on an exam that I posted online. This very first one, we're going to want to name it as a benzoic acid because a carboxylic acid has priority over an alcohol. If it was the other way around, we would name it as a phenol. So, let's see. So meta hydroxybenzoic acid, or you could do 3-hydroxybenzoic acid. Both of those would be appropriate and correct. Then, let's see. This one here is just one of those memorized ones. This is toluene. It looks like it would be methylbenzene, but we call it toluene. This one here is naphthalene, and it's spelled naphthalene. I think that's right. This one, the kind of bigger ring down here at the bottom, that one can't be named using orthometa-para convention because there's 3 groups on it. You can only use that for 2. So I'm going to do the numbering. So that would be, let's see, 1, 2, 6 dimethyl. Oops. And then the parent chain on that is a benzaldehyde. Did I spell that right? Benzaldehyde. Yeah. So, and then lastly, I have this molecule here, which is a butadiene. So that would be 2, 3 dichloro, buta, 1, 3 diene. There we go. So hopefully those names made sense for those molecules. If you got that far, you were doing pretty good. Now, I pulled up do you get extra points for writing both? No, but it means you're doubly not wrong. But it also runs the risk of you getting one wrong and one right, and then what am I supposed to grade? I've seen it happen. So, which one is that on? Kim Sketch. Okay. So, xylene is one of those, special cases where it's just kind of a memorized structure. It's where you have 2 methyl groups instead of 1. So, ortho would be, if I had it at that position, that'd be orthoxylene, but in this case I have metaxylene, which would look like that. Dinitrophenol, it's actually kind of a common molecule, and it's abbreviated DNP. So, and then the nitro groups. 2 and 3. So those are amines as they are written. There we go. don't know if you guys can see what I'm doing on that. You can click, let's see. You can't see everything that I'm doing. If you look where it has that, that A for atom highlight, you can basically go and click that and then edit the label for any atoms that you want. Okay, so para-amino ethylbenzene. So that technically should have been named as an aniline, but that's okay. Let's see, so para. There we go. And then ethyl aniline. Two methyl. 3-iota, and then 2-phenylbutyl. Now this is one that a lot of people have had questions on, specifically how to do phenyl naming. So you're basically just looking to see what has the highest priority. If it's something directly on the benzene ring, then you name it as a benzene. If it's not, then you'll name it otherwise. So butanal, and I've seen some people getting confused in your class specifically. So yes, I'm talking to you. I've seen you guys confusing butanal and butanol. So remember that there's a difference between an aldehyde and an alcohol. So let's see, 1, 2, 3. So a phenyl group would be right. Carbon 2, and I just plop a phenyl on there. There we go. So if you had something that looked like that, you had all the nomenclature right for those things. So I see some of you guys are asking me questions. Let me pull up my chat box. Hi, Jammin' Girls. I made this account in 5th grade. It's Candace. Hi, Candace. Can you show an example of a structure with a nitrile group being named, being priority in naming it? I absolutely can. So I'll go ahead and do that in ChemSketch since I already have that up. Okay. Computer screen. Okay, so let's just put on a group where, I don't know, 1, 2, 3, and a nitrogen. So this is kind of what I encourage you guys to do is, you know, if you're, what happens if I need to name something like blank, and then I draw an example of it, and then you can kind of go from there. That's like literally what I do if I get stuck on something. If you ask me something and I say, I don't know, I go to ChemSketch and work on that. So I can go under here, and then under tools, you can do generate name for structure. I don't have that pulled up as a list, but there you go. So 3-methylbutane nitrile. So you're including the carbon that's part of the nitrile functional group as part of your parent chain, just like you would a carboxylic acid. And a nitrile is considered a derivative, there we go, of a carboxylic acid. Is there a specific temperature range for thermodynamic? Just go warm. So to do the thermodynamic addition controls, just think of something that's warm. So, I don't know, 40 to 100 degrees warm. And then for the kinetic control, you'd be thinking of something like 0 to -15 or so. So like, it should be warm or really cold. You don't need anything like 450 degrees under pressure or anything like that. All right. Candace, I hope that answered your question, just kind of seeing an example of that. I know you have your Mac at home, so you probably don't have ChemSketch on it. So these are some of the other questions from the last exam. So in this example, this is one that would be doing an electrophilic addition reaction. And so you would add in the HBr to this, this ring. It's not a benzene ring, it's a cyclohexadiene. But it's also got conjugated double bonds. It's got 2 of them. And at 40 degrees as your temperature, you would be looking at doing things with thermodynamic rather kinetic than kinetic control. So that doesn't change the placement of my methyl groups, but what it would do is it would put the hydrogen right there, or you could have put it at that spot, leaving a carbocation right there, and then a double bond there. So that would kind of be the intermediate, but then you would get a shift in resonance structures. Let me find my resonance arrows. It's not what I wanted at all. And so you would get your shift in resonance structures. I'd still have my 2 carbon groups. I would now have a methyl here. My carbocation would be there. And then my halogen could come in and attack. So I realize I'm not showing you the actual like arrow pushing or anything, but on this one that's pretty simple. It's the kinetic versus thermodynamic control that's really the one in question here. There we go. So you should have something that looks like that. Alternatively, if you had the bromine down here at the very bottom because you added to the double bond on the left instead of the one on the right, that's fine. It's a symmetric molecule. It doesn't matter. Okay. For sulfonation, will you show me how to use, well, you wouldn't use the sulfuric acid as the base. You would use the sulfate, the hydrogen sulfate left over. So just the conjugate base of sulfuric acid. You okay? Hold on a second. Sorry, I had to scream up to Brandon. The dogs need some water. There's nothing sadder than hearing Onyx licking a dry bowl. Okay. Did that answer your question, Richard, or is that still Janae, or? They need water. Thank you. Okay, until I hear back from... Okay. I'm saying until I hear back from Richard, Janae, whoever it is there, I'll just do the next one. Thank you, dear. There we go. Jasmine, I'm going through the entirety of the old exam as people are waiting to give me questions, so I'll get there in a bit. Dennis, the halide is a kinetic or thermodynamic? Well, you tell me. What do you think? Thermodynamic is the one that you'll get resonance to form the more stable product, whereas kinetic is the one that will form the fastest reaction and doesn't undergo the resonance. So for SNAR you can put heat, that's fine. Or you can put like 350 degrees or 300 degrees, whatever you want. Alright, so looking at this reaction here, we're looking at one of the Diels-Alder reactions. Pull out my paintbrush here. Methyl groups. I told you guys I always line mine up this way. I wasn't joking. I think it's just easier to see if you do it the same way every time. Oh, I didn't do that well. Let me fix it. When I said that I do it the same way every time, and then I didn't do it the same way every time. There we go. I never quite got to covering endo products versus exo products, so I'm skipping over those. But if you read something about that in your book, it's a thing that can happen. And so now I would have, and it, you know, it's again helpful if you go through and kind of number everything. So those would be the 6 carbons that are part of your ring. So 6 carbons. And then we have this one here and this one here as the bridge head. I've got 2 methyl groups coming off of that. There's a double bond there still between carbon 2 and 3. And then at carbon 6 here we would have that carboxylic acid. So that should be what your product looks like for that structure. Careful, that looks... select, see if I can get rid of that. Okay, it looked like a double bond there. So you should have something like that for your product. If you like to draw it flat, so let's see. And then you would have a CH3 there. Another one coming off there. Sorry, it's kind of little. And then the carboxylic acid. So you should have something that looks roughly like that, but perhaps with better... Here, we'll do it this way. Line CH3. CH3, line. There we go. So those would be attached to those 2 carbons there. Okay. Like that. Tiny for you to stare at that for a second, and then I'll get the next one. Oh, the next one had a typo on it. I'm sure you guys probably figured that out because you were looking at it wondering what the heck's going on here. So I don't know, there ended up being an extra arrow here, so just kind of act like there's only one arrow. I did see some people had some like pretty creative things in that spot, so, but this is fine. So over your first arrow there, you're basically going to need to do a kinetic controlled electrophilic addition reaction of HCl. So HCl, and then you need to keep it really cold, so like 0 degrees Celsius. Wow, that's really tiny. So that would basically be your first reaction to give you this product. And then the next reaction condition, that is an anti-Markovnikov addition of water, so anti-Markovnikov hydration, so that's the borohydration reaction. So BH3, tetrahydrofuran is always a solvent for that. That would be your first set of stiff. And then your second set of stiff would be H2O2 and hydroxide. Yeah. So if you had something like that for that reaction, you're in good shape. If you had something creative done in here because there were 2 arrows and I didn't tell you that there was a typo on there, then you're in good shape. Okay. So an example for one of the 3. So one of the oxidation reactions. Sure, we can do an example of that. Swap my screen over. So you're talking about oxidation reactions. So if I have an alcohol, and we can do one of each. So I'm going to abbreviate Des-Martin as DMP for Des-Martin periodinate. We'll do pyridinium chromochlorate. And then I'll have CrO3. Okay. So if anybody's looking at this one and saying, I thought chromium 6 oxide only works with a primary alcohol, you're correct, and we would expect no reaction for that. The second one, which I wouldn't give you on an exam, a no reaction. I don't think I've ever given one of those on an exam. And then the pyridinium chromochlorate and the Des-Martin periodinate would do the same thing, which is just oxidize it down one step from the alcohol to the carbonyl. That's it. We didn't learn a mechanism for it. I'm not holding you responsible for a mechanism for it. You can find it online if you're interested. You can do that. So hopefully that makes sense. If I had something, oh goodness, that's not what I wanted at all. Carbons and an alcohol. If you went through and did any of those reaction conditions, so the Des-Martin periodinate, the draw button, text button, the Des-Martin periodinate and the praseodymium chromochlorate would give you the same product. It would be the aldehyde, so that was 1, 2, 3, 4. I always do 6 carbons. I don't know why. If you guys hear my dog snoring in the background, I'm sorry. It's like zonked out on the floor. Okay, so that would give you the aldehyde, and then if you did it with the chromium, you would get the same thing, except it would oxidize it one step further down to the carboxylic acid. If you want, you can draw the hydrogen there, but you don't have to. There we go. So hopefully, oh no, what have I done? Okay, here we go. So hopefully that answers your question about that. It wasn't a very super in-depth question, so hopefully that makes sense. Do we need to know how to make bicycles for butane or anything else other than cyclohexane or pentene? Yes, you should be able in theory to do bicycles for anything. If you understand how it is, then that's what you got. Usually what we're going to be doing is for cyclohexane or pentene, because those are going to be the easiest ones to have a diene involved. And so far I was only showing you guys the reactions that have the diene is the ring, whereas the dienophile was not a ring in each case. In theory, you could do it the other way around as well. So just kind of realize that. Change a certain part in the middle to get to the product. What's that? Oh, it's Candace. Okay. I couldn't remember if it was Carly or Candace. Yeah, Candace, I can't tell if there was a lag that led to that question popping up late or if I answered your question or not. So let me know if there's another question. Okay. Okay. So I'll go ahead and do the next one down on the old exam. It's a pretty simple one. Bigger. So this is just a Friedel-Crafts alkylation reaction. We would expect, because we have an alkyl group there, we would expect a mixture of products. You would expect the ortho substituted, and you would expect the para substituted. If you drew ortho substituted over here instead, that's perfectly fine. Just pick one, it doesn't matter. But that's that reaction right there. The next question was how to make this molecule from benzene. And so that's really just getting in, buddy. That's really getting into the concept of knowing when and how to do benzene reactions, since they can give you different specificity, right? So we have two things put on there, a sulfate and a bromine. And so bromines are, we have to look at that and say a bromine is going to add things in an orthopara fashion, whereas the sulfonic acid would add things in a meta substitution pattern. So that means we need to add the sulfate on first. So gonna do this, that SO3 and H2SO4 are generally what you would use for the first reaction. And then the second reaction would just be bromine, diatomic bromine. And iron, whoa, that's not what I wanted at all. Let me try that again. There we go. And then iron tribromide. So that would be the first reaction there. And then the second reaction was to make this molecule there. Now, we did not learn any direct ways to add an amine directly onto benzene. We did two different possibilities. So one of them, we'll do two different possibilities here. One of them was to take, and actually I need 3 arrows. Sorry. Hopefully this isn't too convoluted looking. So the first thing we could do is do a nitration reaction. And so that would require the HNO3 and the sulfuric acid. Then the next step would be to either basically just do a reduction of the nitration product, the nitro group. And so I showed the class that we could do that in the following way. You could do a reduction. Is that not big? We didn't learn the reagents for that. They're actually in your book. You can look them up if you're interested. But we just said we could just look at it as an oxidation or a reduction reaction. And then the last step then would be to chlorinate. And if you had an amine there, you could chlorinate, and you would expect to get some ortho and para product in that case. So that would give us the ortho that we're looking for. So Cl2 and FeCl. The other reaction would be kind of similar, but it would be doing a chlorination first. Then we would do one of those, the SNAR reactions, the nucleophilic aromatic substitution. So if you remembered, that required like 350 degree temperature, lots of pressure, and something like NH2. That would put the amine on the ring and displace the chlorine. We still need a chlorine on there, so then we could just go back through again and do another chlorination reaction. So if you did this in either of those two ways, they would both be 100% correct. I have no problem with either of those sets of reactions. So hopefully that makes sense. I don't think we've gotten any more questions, so I'll just keep going. Whoa. If you've gotten this far, I'm giving you a heart. There we go. And I don't just mean this far in the video, I mean this far in the semester. you've done a lot of organic chemistry at this point. The next page are the mechanism pages. And I generally like to do those, whoa, too big. On sketch, just because I think it's a little bit easier. So, those of you who are in lab are well aware of the fact that drawing a mechanism in Chem Sketch is not impossible, but it is not quick. So, wow, that looks terrible. If anybody's curious about what I'm wearing, I was really cold, so I'm definitely wearing a Jack Skellington onesie right now. It has the bow tie and everything. It's very cute. Check this out. I can see you because it has holes in the eyes. But I won't do that. I don't want to give you kids nightmares. Okay. So when we have really high pressure and really high heat, bases can do what bases normally do, which is act as bases and deprotonate. And when that happens, you're basically going to kick off a leaving group in the bromine. And that gives us a terrible, terrible structure. And if you guys hopefully remember, so benzene has double bonds, right? Benzene has a triple bond, so that's the benzene structure. And then the benzene structure is incredibly prone to nucleophilic attack. Okay, sorry. I muted you so you didn't have to hear me sneezing. Hopefully it worked. Okay, so then, so it's prone to nucleophilic attack, as I was saying. So you can have a system kind of like this. If you have hydroxide, you're going to likely have water, right? So you have a source of protons floating around somewhere. And that would give us the phenol product. You were wondering what, Richard? Oh, what I was doing? Yeah, I was sneezing. Okay, so hopefully that one makes sense. It's a pretty simple mechanism. After I've, scared the fear of God into y'all and told you that, like, we can't do anything with benzene, then I give you a bunch of reactions we can do with benzene. But again, we've had to make really strong, electrophiles, or we have to put it under crazy temperatures and pressures, and so it's not a trivial process, and it's just that whole, resonance stabilizes everything thing. Aromaticity is a stabilizing force. Okay. The nitration on the methyl, on the toluene, I think I'm going to skip over that one because we did pretty much that exact one in class. So now I'm looking at one that says, how can you tell when something is a catalyst? And, I'll be honest, your all's class has been kicking a lot of butt on that, because anytime I look at the board and I'm like, where's the catalyst? Like, the whole class can pick it out. So, the definition of a catalyst is it starts a reaction one way, and it ends the reaction the same way it started, so it completes what's called the catalytic cycle. A lot of what you guys have seen have been metal catalysts or just acid or base catalyst, and it doesn't get consumed in the reaction. It lowers the activation energy. Those are all kind of definitions, but you can tell if it's a catalyst because you end and get it back when you're done. There are some very, very, very expensive catalysts out there. I've probably told you this before. Where you're talking hundreds of dollars a milligram because they're rather large and they're synthetically challenging to make. And a lot of them will involve, precious metals and things like that. So some people will literally go back through their reaction when they're finished, and instead of just saying this was the non-organic garbage that I wanted, that I didn't want, you'll actually purify back out that catalyst because they're so expensive. Okay, the oxidation state of a carbon in benzene. We did not talk about oxidation states, so I'm just going to have you guys skip over that. And then last but not least was, let's see, paradiethylbenzene, and looking at a proton NMR for that. Again, that's something your class has been doing quite well in, so I'm not terribly worried about your abilities to do this one, but we can still do it. My finger's like not wanting to work on the... Okay. Oh, I know what's going on. It's because I zoomed into like 200, so it looks gigantic. There we go. That's better. So if we were looking at NMR, that would be about our 0 point, that would be our 10 point, that's about where we would expect for a proton NMR. You would expect, let me see if I can get like big fat dots. I think I can get big fat dots. So, sorry, I just made a weird noise. There we go. So these four would actually be all the same because the molecule's symmetric this way and that way. So you would actually only expect to see one peak there, and it should be like a doublet. It might be a complicated doublet. Then the ethyls, you would expect to have the CH2 group that's next to the benzene ring, you would expect it to be farther downfield, and it would be split as a quartet. And then you would expect a triplet for the CH3 group. So something that looked roughly like that would be good. Okay? So Jasmine, you said number 12, I think. I don't know if I got the one that you had a question on or not. Hopefully I did. Let me know if there was another question and I did not get it. My bat cape. Yeah, well, I'm not Batman, but I'm Megan Man, and I have a bat onesie, so... Oh, the one with the extra arrow. Yeah, the one that had an extra arrow. Yeah, usually at this point, especially if you guys are looking at your stuff and you're like, this doesn't make any sense. It was probably a typo, let's be honest. I am prone to typos. The good news is if I don't catch them on an exam, then I just give you guys creativity points for being creative on those responses. All right. So that was the old exam, and I've answered a couple questions, but if you guys want, we can, you have me for another 20 minutes or so if you have other questions in particular, or if you just were curious about something, or let me know. In the meantime, we can do doggy cam. Hi, Twinkie. Say hello to my class. Hey, camera shy. This is my dog with the weird little legs. He's shaped very much like a sausage. I'm going incognito mode. It is quite a warm onesie. My mom got me this for my birthday. You know, the great thing about The Nightmare Before Christmas is that it's the holiday movie that you can watch twice a year, both at Halloween and at Christmas. That makes it pretty unusual, and I like it. I would love it if you guys never saw me in a onesie. But in the winter when it's cold, let's be honest, that's pretty much what I wear when I get home. Maybe next time I'll put on my Grinch onesie. I have a Grinch onesie. I don't know why I can hear Janae right now. God damn it, I don't want to hear about your onesies. Do some chemistry. Shit. Please tell me you stabbed yourself with a clean needle and not one that was infected with, like, dog gonorrhea or something. I don't know. You do weird things at work. You're welcome. Thank you for your service to the veterinary community of Clarksville. You've been vaccinating cows. You know, I sometimes say that as a college professor, I have a weird job, you know. Some weeks I work 60, 70 hours, especially if there's a lot of grading. Some weeks I work like 30 hours if there's, you know, not a lot of grading or research, you know, it might be 20 hours a week. And then I get these huge places in the end of the semester where it's like 60, 70 hour work weeks just from all the grading and everything. And in general, it's an odd job, you know. It's weird to stand in front of a group of people and talk about chemistry all day. But I don't think it doesn't hold a candle to anything that you do, Candace. I would like to think the entire class would agree with that. We've heard enough stories at this point. We know. You've done some weird things. I wanted to ask kind of a thought question here. Sorry, excuse me. I'm doing this off camera so you don't see. Okay. So, let's say that we have this methyl nitrobenzene, or you could call that a nitrotoluene if you want. What would happen if we tried to chlorinate it? We have two directing groups on there, right? This is just kind of a thought question. And if you did the problems in the book, you've already seen ones like this, but I know some of you guys don't like doing those problems. So I want you to think of it this way. Let me grab my big brush again. So the nitro group is going to push things in the meta position. So this position here is meta to nitro, and that position is meta to nitro, right? Then the methyl group would be pushing things in the ortho and para direction. So I will mark that with an X. That would be ortho. There's already another one at the other ortho position because the nitro is already there. And then that would be para to the methyl group. So then, would it make sense, my friends, if we got CH3 and O2, that's supposed to be a Cl, and out of room. Those should be the two products you would expect for that. So when you're doing these, especially these electrophilic aromatic addition reactions, you know, you can just kind of think about the directing groups and kind of couple them on top of each other. I don't like how it's like cutting off half my face. So, just another thing to think about. If you were wondering, that's like the thing that, you know, Dennis would ask in class. Grace would be thinking it, Dennis would ask it, Richard would roll his eyes, and Janae would yell at everybody to not talk about stuff like that. You know I'm right. And I wouldn't have you any other way. Are there any more questions? Some of you guys are being awfully quiet. I see that there's 12 of you talking, or 12 of you on here, and only like 2 of you keep chatting, so hopefully I have gotten the questions answered that you came here to ask. Mix, are they not in resonance? Oh, so Richard, if the substituents were 1,3 instead of 1,2, then you can often end up getting either a bigger mix of products or like not really any products at all. Unless you like really up the reaction conditions and use stronger stuff, which I would never ask you anything like that. And then when there is a mix, they are not in resonance. It's like one and the other. So remember, resonance and isomers aren't the same thing. So there would be resonance. Let me do this. Pull that back. I'm assuming you're talking about these two molecules here. So the electrons in the ring will still be going around, right? But the placement of the chlorine, the methyl group, and the nitro group won't go anywhere. So those would all still stay the same. But you're absolutely right. There would be resonance going around the ring there. Oh, Stacy, Dennis, Richard, Zella. Zelly, I think you mean? We don't have a Zella. Janae. Although I do like Zella, that's a fun name. I do know a Zelda, and I know a Stella. So it's like Zella is if Stella and Zelda had a baby, right? What have I done? Okay. Are you guys all sitting in one of the big lecture rooms with me on the screen? Because you've done that before, and I find that very disconcerting. Well, before we get off, I want to show you guys something because it's sitting next to me here and nobody's asking any questions. Back when I was your age, I took organic chemistry and fell in love with it. I was really afraid of it at first. I thought I was going to fail everything. It was an 8 a.m. class. the guy that taught it was known to be a monster. He had a reputation. And this was the book that we used. Seihan Ege's Organic Chemistry, Structure and Reactivity. This is the 4th edition. And I have often found myself going back to that book. I think it's probably my favorite book. I've used it and highlighted it and thought more reading that book than any other book I've ever had in my life. Academic and non-academic. And that you all know as a class that I have a diabetic dog. My diabetic dog is 100 pounds. He's a thin 100 pounds. He lost weight when he got the diabetes. But big dogs drink a lot of water. Diabetic dogs pee a lot. And so sometimes he has accidents, which isn't a big deal because I have tile floors. I left my beloved book on the floor. And last week I came home and it was sitting in a puddle of dog pee, red peed on my book. And I was heartbroken. And I realized that this was like the most important book that I'd ever had in my life, because without it I might not have fallen in love with organic chemistry and gone and studied it in grad school and become a professor teaching it to you guys. So I thought, man, that's an old book. It's like from 1998. But I need a new one. I got a new one on Amazon for $10. I don't know what happened. Well, I feel silly. I was talking to you guys for like minutes and minutes and minutes, and then I looked and it said my stream had stopped. So anyway, it wasn't anything important. I was just telling you about how my dog peed on my book and I had to go buy a new one and it was only $10. Thanks, Jasmine. Yeah, we can do another bicyclic problem real quick. You're not the only one that has trouble seeing those. Oh, I should have brought my model kit home. I need to just have a model kit at home with me, and I never think to bring one, and I've got like 4 in my office. So I'm sorry. Maybe at some point somebody remind me if they see me leaving the building, say, go get a model kit and take it home with you. Okay. So thinking about bicyclics, so that would be a weird way of drawing cyclopentane, right? It's basically drawing cyclopentane with one piece of it like puckered up. There we go. So that's a weird way of drawing cyclopentane, and we would never draw it that way by itself, but if it's in a bicyclic structure, you might have to. So here, there we go, there's another one. So in that case, if you were looking at it from the top down, looking like from the bridgehead down, you would see something, wow, that's terrible. You would see something like that, where that one there is that one there. The most important thing when you are looking at a bicyclic, I think, the easiest way to do it, is kind of lump it into 4 different areas. The camera inverts the image, so if you see my hands in there, I'm trying to like figure out where to put them. It's because I can't do that in my head. So the way that I like to think of it is I group it into that thing, that one, and that one. Okay. So essentially, right here, I'm looking at 2 carbons, and those are the carbons right there that I'm bolding. If I look at these 2 carbons right here, those are right there. Okay. If you look at the bridgehead, you should be able to figure out how many things there are, how many atoms there are. So that one has 1, so it would just be a peak. If it had 2, we could draw it like that, and that would be the 2 atoms involved in that. And then the rest of it's kind of just putting everything together. So if you are trying to do, for example, a Diels-Alder reaction where you would expect to get some sort of bicyclic product if you started with a cyclic product, or a cyclic starting material. So I can start off with, let's do cyclohexene, cyclohexadiene, and then let me change my color. I'll just make it simple and put next there, okay? So what I need to remember is that I can lump this into a couple categories. This here is going to be one of those categories. This here is going to be another one. This will be one, and this will be one. So it's kind of looking at everything in these kind of groups, okay? So I'm going to erase those circles and then say, if we have, and can I do this? If I have that one there, okay? I can just draw that. What's it connected to? Well, it's connected that and that, so, okay. If we wanted to number these, I would have 1, 2, 3, 4, 1, 2, 3, 4. Okay. Now with the Diels-Alder reaction, we know that this here is going to bond there, and that's going to bond. Okay. So I can show that as another 2 carbons. These 2 right there, hopefully you can kind of see me bolding that one. And so then what's left are these 2 carbons here, which are the bridgehead, and they come down like that. So when you're looking at one of these bicyclics, scoot back so you guys can behold the onesie, but also see my hands. So, you know, normally we're used to seeing the chair conformation being kind of like, you know, half up and half down, and it flips back and forth. When we're looking at it like this, we're looking at it more like this, with one coming up out of the top, okay? Oh, God, I hate this. I can't do it, guys. I'm special. I'm trying to show cyclohexene kind of being a cup. There we go. So this part here that I just circled is kind of like the cyclohexene here and coming up. And if you look, that's 6 carbons right there. 1, 2, yeah. So let me highlight that in burgundy. That itself, 1, 2, 3, 4, 5. That is 6 carbons, right? That is a cyclohexane. It's not in the chair conformation. It's in this weird little, like, cup-looking thing. So the 2, and this would have the double bond there. That would have my halogen, whatever my halogen would be. Doesn't really matter at this point. But that's kind of how I go about looking at these. And I realize that it looked like I just drew some sort of like pop art, and it doesn't make any sense. I'm hoping it made sense when I was kind of talking about it. But you know, you have to break it into pieces that you can see. And if you guys want to bring a model kit tomorrow because it helps you with these, absolutely do it. You know, I think they're great. You know how I love my model kits. But, like, let's do another one real quick. And then I'll let you go back to studying so you don't have to keep sitting here staring at my face all night. So, let's do one like this. So this would be a very typical product for Diels-Alder reaction. So one thing I could ask is convert that to a three-dimensional structure, because it's really not. It's more of a, you know, flat structure that's meant to look flat. I mean, it definitely doesn't look like it has much dimension to it, and it's drawn that way on purpose. So again, dividing it into kind of those 4 different categories, I would have kind of this area here. So I draw 2 carbons and I can put the double bond there. They're connected to that and that. Those are the next 2, right? Those are connected to these 2. So I'm kind of looking at it as a flat structure, right? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Carbon number 5 has that aldehyde hanging off of it. And then what I have to look at is between 3 and 6 here, I have 2 carbons. So that would mean I have a 2-carbon bridgehead, okay? So that's one type of question that, you know, you could ask. The others are all just, you know, basically drawing Diels-Alder products. But like here's a good bicyclic. And you can have tricyclics too. You know, I'm not going to ask you to draw any like that. But like that itself is a bicyclic. It's called bicyclononane because it's combined got 9 carbons. You know, you can kind of draw these in sort of different perspectives. Here we go. So if you kind of draw that chair first, it's kind of easier to draw it that way. It's kind of the same thing, just tilted a little. This is not a possible product for a Diels-Alder reaction because you basically wouldn't have had 2 conjugated bonds to make this. But, you know, just another example. And you could have sorry, hold on. So that's one there where you basically had a cyclopentane and then you added another carbon onto that. Again, not something you could do with a Diels-Alder reaction because you would have to have 2 carbons there to add in like that, but, you know, just another example of a bicyclic. So, you know, it's all about kind of looking at it and recognizing those different components, I guess. I hope this is making sense. I'm not getting any feedback from you guys, though. Did I go offline again? No, it says on live. It's funny how much I rely on y'all's faces normally, and when I'm doing this, you can see mine, but I can't see yours, so I have no idea of what I'm saying. It's like resonating at all with anyone at all. It's amazing how little I can do when I don't have Janae cussing at me. Thanks, Anna. I was like, it makes sense. Sure. Okay, thanks, Jasmine. Well, I'll let you guys go then for the night. I think I just spent 15 minutes trying to show you guys some bicyclics. If you have any other questions, I'll be up for a few hours, so you can feel free to email me. If you're coming in late to this and you are wondering if I saw your email about looking over your old test materials, I put those in this video, so as soon as YouTube gets done doing YouTubing on it, I will post it. I think I may be able to throw something together now. You're welcome, guys. And I will see you bright and early at 11:15 tomorrow. So, I guess, yeah, I should have these graded by Friday. I should be able to have them graded by Friday. Yeah. I won't have office hours tomorrow afternoon, just an FYI. There's a baby shower. One of the ladies at Brandon's school is having triplets. So I'm kind of going to show up for that. I mean, like, not at the birth. Like, that's not what's happening. They're just having the baby shower. But part of it is because I really like her, and the other part is I'm curious what a pregnant woman looks like who's having triplets. It's a lot of baby. Yeah, that's a lot of baby. So you are all welcome. I see you with your thank yous. You don't have to thank me. These are just nice office hours that I can do in my pajamas from home. That's how things work. And I will see you all tomorrow.